as you can see from the title of this video, this tutorial is about branches of chemistry and the scientific method. One of the very first things we'll learn about all year is what the study of chemistry is and how we can break it into different subdivisions based on what it is that you are trying to accomplish in your research. Starting out simply, chemistry, by definition, is the study of matter and the changes that it undergoes. This definition makes chemistry what we would call a physical science. If we looked at the different branches of chemistry that are out there, we can break it down into 6 subcategories. The first of those subcategories is called organic chemistry. Organic chemistry focuses on only one element from the entire periodic table, and that element is carbon. The reason that there is an entire branch of chemistry devoted to one of the 120, roughly, elements that are out there is that a very large percentage of the compounds on Earth are made up of this particular element, which is carbon. So organic chemistry studies carbon and any compound that carbon can form. So the study of carbon compounds is what we call organic chemistry. What we'll focus on in this class most of the time is what we call inorganic chemistry. Inorganic chemistry focuses on carbon a little bit. It doesn't ignore it, but it also involves the other 100 and so elements that are on the periodic table. So it is the study of what we refer to as non-organic substances. Non-organic substances sometimes involve carbon, but most often non-organic substances are the other elements on the periodic table, things like hydrogen and oxygen and nitrogen, right, and uranium and many other elements that you may have heard of along the way. The third branch of chemistry is called physical chemistry. Physical chemistry is defined as the study of changes of matter and its relationship to energy. Now, you'll learn later that matter is anything that has mass and takes up space, and it's shown up in a few of these definitions, so I want you to hear it. But physical chemistry focuses not on what the properties of individual elements are, but in particular, energy that's associated when things change about elements or compounds. Particular branches of physical chemistry that you'll see is sometimes physics plays a role. There's a lot of math in that particular topic. People that study explosives and things of that, you can see there's a direct relationship between a chemical reaction, a combustion of dynamite, TNT, and it comes with a relationship to energy because the explosion that you feel is a large amount of energy that is released. A physical chemist would not focus so much on the what is happening with the reaction, how is trinitrotoluene, TNT, turning into carbon dioxide and oxygen, but rather how much energy gets given off when it does so. That is what physical chemists tend to do. Fourth branch of chemistry is called analytical chemistry. Analytical chemistry is the study of compound identification and composition of substances. Analytical chemists and forensics chemists, or forensists, many times can be one and the same. Right? If you are wanting to identify an unknown from a crime scene, if you want to test 2 samples to see if their DNA matches, an analytical chemist would be a good person to take that to. That is what they do. They identify compounds, particularly unknown compounds, and try to compare them to known things to see if they match. The other thing they'll do is they will take known substances and look at their composition so that they are able to create large databases to see if those known substances can be used to identify unknowns. The fifth branch of chemistry is a relatively newer branch of chemistry in the last few decades called biochemistry. Biochemistry is the study of chemistry, but it is specifically within living organisms. Bio, like biology, meaning the study of living things, and then chemistry. So it's chemistry within living things. Biochemistry tends to be a very popular major for pre-med students because it involves a lot of biology, which they'll need for their anatomy and whatnot, but the chemistry background to things as well. Biochemists will study things like metabolism and things that relate to how your body breaks different chemical compounds down. The last branch of chemistry is called theoretical chemistry. Theoretical chemistry uses known properties in mathematics to predict properties of new compounds or at times undiscovered compounds. Analytical chemists tend to compare. They'll take an unknown and be able to tell you what it is if it is a known substance and compare them. Theoretical chemists will look at large banks of known substances and then postulate on will those known substances lead to a pattern that we can predict properties of something that will be similar yet undiscovered. So theoretical chemists tend to use mathematics and extrapolation techniques to predict things about yet discovered compounds and elements, which there are some that are still out there, and you'll find there are actually very, very many that are still out. The second thing I wanted to talk about was something that you've probably heard about a lot of different times called the scientific method. The scientific method is simply a strategy used to observe, gather, analyze, and communicate information. That's good in itself, but the scientific method is used specifically with the goal of solving a problem. We want to figure out a question and then use a very systematic process to try to come up with an answer to that question. Many times the scientific method is taught in steps, like you follow step 1 to 2 to 3 and so on. What you'll see from this next board is that it's not quite that simple. If we were to draw kind of more of a flow chart of how the scientific method works, there are most definitely landmarks along the way which have been called steps in the past. However, you'll see that you never tend to just follow it in one direction. Data collection and solving problems is not as clear-cut as sometimes it's portrayed in your younger ages. So, we're going to look at the main components of the scientific method. The first thing, and where all things start, is you have to make an observation. You need to witness something that piques your curiosity enough that you want to find out an answer to it. You see something and you're saying to yourself, well, why does that happen? Or what was it that I just saw? So when you make an observation, believe it or not, you are already gathering data. And there are two types of data that you can gather. We call them qualitative data and quantitative data. You're going to learn this is a very common theme in chemistry. They'll take two words that look very similar to each other, qualitative and quantitative, yet they mean two entirely different things. The best way to break this down is if you look at the words. When you look at the word quantitative, we start with the one on the bottom. When I look at the word quantitative, most people, if I ask this in class, will say that looks like the word quantity. And when I ask you what you think about when you see the word quantity, most people will say they think about how many. They're counting things. Quantitative data is just that. It is numbered data. So if I said I have 7 pens, that is a quantitative piece of data because of 7. If I said that a person weighs 157 pounds, the fact that it is 157 makes that a piece of quantitative data. If I look at somebody and say they are very skinny, that is not a quantitative piece of data because it does not involve number. It involves a description. That pushes us into the second category, qualitative data. Usually when I ask in class what the word qualitative looks like, people say quality. And when you describe quality, what you're really doing is describing what something looks like. So qualitative information is non-numeric data. Right? I have a blue shirt on. That is a qualitative observation. I have brown hair. That's a qualitative observation. I have a black laser pointer. Qualitative observation. I have one shirt on. Quantitative observation. And sometimes you'll be doing both at the same time. I have one blue shirt on, one making it a qualitative observation, blue making it one making it a quantitative observation, blue making it a qualitative observation. So you can see that there are two different types of data collection that we do. Once we make our observation and we want to come up with a solution for something, we come up with a hypothesis. Now, when you learn about a hypothesis forever, they always say a hypothesis is an educated guess. We have learned to get away from that definition because what you're going to see about a hypothesis is that a lot of times it's very uneducated. Right? People only have made limited observations and they're going to try to come up with a solution. I go out to a baseball game, I watch the pitcher throw one pitch, it's a strike, so I hypothesize that he is a great pitcher. That may or may not be the case. It's not very educated based on the one thing that I have seen. So we will define a hypothesis, right, as a proposed answer to a question. Right? We have not done nearly enough research to say if it is educated or not. So a hypothesis is simply a proposed answer to a question. Once we come up with our proposed answer, we want to check to see if it has some type of bearing. So we test it with an experiment. That's what chemists do. That's what all scientists do. You got into this type of research because you like to get in the lab, you like to do hands-on things, and you want to test to find out what is going on. So we test the hypothesis with an experiment. During that time, you are gathering tons of qualitative and quantitative data. Testing, testing, testing. Once you get all of that data, you are going to analyze it and begin to make conclusions. And when you go to make your conclusions, one of two things can happen. First thing that can happen is your hypothesis is supported. The data that you are collecting tends to agree with your hypothesis. I go and watch an entire baseball game, and I have that person throw 200 pitches, and 175 of those pitches are strikes. My hypothesis was that he was a good pitcher. Well, my hypothesis is tending to be supported because 175 times out of 200, he threw strikes. Once that hypothesis gets supported, it's not enough just to support it one time. You have to go back up and begin to retest. You make him come again and throw 100 more pitches. You make them come back a third time. You make her come back a fourth time. And so on and so forth. Till you have gathered so much data supporting your hypothesis that now, after you analyze it and continue to support it again and again, you have the ability to develop a theory. And a theory is simply a principle that explains a body of facts. I had a person come and throw 10,000 pitches. This many of them were strikes. That's my fact. And my principle is that that person is a good pitcher. Once that happens, right, again and again and again, we tend to call it a theory. And there's lots of theories out there. Right? The theory of relativity is one of them, for example. Right? There are many, many theories. On the other hand, I can gather my data, analyze it, and I'll see that my hypothesis is not supported. Right? I will take that person, and after seeing them throw one pitch, I'll say, I believe them to be a good pitcher. I'll have them throw 100 more, and 99 in a row miss the strike zone. So what happens is my hypothesis is not supported. That doesn't mean I say, oh, well, there's no point in doing this anymore. I was wrong. I give up. That's not how the method works. What you do is you fix what the real problem was. The problem wasn't that your data didn't support what you thought. Your problem was that your answer to your proposed question wasn't accurate. So what we do is we go back up to this step and we revise our hypothesis. We come up with a new hypothesis, and at that point my new hypothesis would probably be this person is not a good pitcher. Then what happens is you keep revising and testing. If you revise your hypothesis enough, hopefully it'll begin to be supported and you retest. And then eventually you'll push on into your theory that explains a body of facts. The last thing I have jotted down here is that a theory cannot be proven. Laws are things that we accept as finite, never ever changing. They exist. The law of gravity. We'll learn about laws of conservation of matter and mass, right, and energy. All right? These are things that are accepted to be true. A theory cannot be proven, right, because there are many times through technology that a theory that may have been accepted for a very long time will be contradicted. You will have the ability to gather new data, and that new data makes your hypothesis not supported. A great example of this has to do with astronomy. When we first started looking at planets and things that we could see from the Earth, the main theory was something called a geocentric model. Everybody believed that Earth was the center of the universe, and that for 1,500 years they had data that supported it. They knew that moons and other planets were moving around the Earth. They knew that the sun moved in the sky. So there was lots of data that supported that idea, and they came up with a theory, right, that was supported by the most famous scientists of the time, like Aristotle, and they said that a geocentric model is the correct model. That is our theory. It explains everything we're seeing. Then, in the 16th century, a guy named Copernicus came along, and Copernicus said, I have data that suggests the sun is the center of the universe. And he started using all sorts of mathematical calculations and proving things orbited not in circles, but in an elliptical fashion. And he came up with something called the heliocentric model. And that, what we have decided now, since 1500 up till today, is a better theory than the original geocentric. So our new theory, right, is that we have a heliocentric model to the universe. Again, even that can't be proven. We have data that suggests it, but you never know. Maybe our sun is part of an even smaller, right, solar system. If there's something hidden inside, you don't know what's out there. That is what I mean by theories can never be proven. So I hope this helped you out with some review or whatever it is that you were going for with your branches of chemistry and the scientific method. You'll see that we're going to use this as a springboard into many other topics here in this chapter, particularly the idea about matter, which will be coming up. As always, if you have any additional questions or you are confused about anything that you're seeing or want to learn more about something, please do not hesitate to come in and ask.